Hello, on November 27th. Alright, let's do this. A 70% passing rate on the problem that I've done before. Maximum number of k divisible components. There is a undirected tree with n nodes labeled 0 to n minus 1. You're given an integer n and a 2D integer array edges with length n minus 1, where edges I is an edge between AI and BI in the tree. You are also given a 0 indexed integer array values of length n, where value is I is the value associated with the ith node and an integer k. A value split of the tree is obtained by removing any set of edges, possibly empty, from the tree such that the resulting components all have values that are divisible by k, where the value of a connected component is the sum of the values of its nodes. Return the maximum number of components in any valid split. So we want to do a split such that the remaining, when you add them together, is divisible by k. So in this case, we remove the edge connecting 1 and 2, resulting split value, because the value of the component containing 1 and 3 is valid. 0, 1, 2, 0, 1, 2, 3, 4 plus 8 is 12. And then the remainder is 1 plus 0, 1 plus 1 plus 4 is 6. I see. And we want to find the maximum number of components of a valid split. Maximum number of components of a valid split. So if I do split on one of them, oh shoot, if I split, so let's say we go from the root down. Okay, we go from the root coming down, and at each position I'm kind of trying to use the same thought process as we used yesterday, because we can say at each root, at each position, do we split or not? But splitting doesn't necessarily mean that it's a tree. So if you split, you will create a subtree. You will create a new component. Okay, so that is good. So whenever you do a split, yeah, it's more than just a split. It's whenever you decide that a child, whenever you decide you're gonna sever from a child, you're creating a new component. because it's a tree. Okay, that's understandable. And then you're coming from the root down, right? You can, like if you go DFS, you keep track of the sum you have so far. But the decision to make is whether we should split or not. The question is, if I split here, will the remainder, or what's the max number of components can I get if I split? Right? Because for each node we can split left, and then we can split right, and we can split both. So for each node we're saying, should I split? Now we say if I split left, now I can say like I can split both, right? If I split both, then I need to know what is the component that contains me. Yeah, I need to know what contains me. So when I split, I know if I split both left and right. Oh, I didn't even say it's a binary tree. So you can have multiple child. Yeah, I just say an undirected tree. So I could have more child, but I think that doesn't matter. Binary tree or not binary tree, that shouldn't matter. Oh my god, this is not working very well. I'm trying to cut my nail right now. I thought I can do two things at the same time, but I'm not doing my nail right, nor am I thinking about this problem right. Yeah, let me just do my nail first. I'm already deep into it. Okay, one leg is done. Let's go for the other foot. Man, my right foot is so much more messed up compared to my left. So much more messed up. It's like all the toes on my left looks healthy, but none of the toes on my right looks healthy. feel like one day I have to pay for it. One day. And I kept pushing it back. So I don't want it to be this day. Okay, that's considered done. Not my best work, but it's good enough for now. Oh my god, I need to clean my floor. But this is necessary because my toenail gets long, and then when you do the jerk, I put my right foot forward and the toe just gets slammed into the shoe, and after a while the toe feels a little bit raw. Okay, so I have a tree, right? So at each position I can choose to just split here. Okay, then the question becomes, we'll do this by itself, and then we do this by itself, right? And then I can also choose to sever here, so it's like two choices. Of course, we can also say we cut both, just like in this scenario. But every node, if you go through this, I wonder, what do you want to get? Like the maximum of this, the maximum of this. The maximum on the left hand side. some edge must be severed. What we need to guarantee is after an edge getting severed, the remaining is still, there will be the minimum that you can sever, right? Basically, we break them up because we want a maximum number of components, which means each one is the smallest you can break. If you keep breaking, it's not gonna get divisible. So but even if you find a small component that's divisible, and you sever it, how do you guarantee that the other part can also be divisible? Or, I don't know. I don't know. And it's not a path, right? It's not a path. Yeah, we can pick 0 as the root. It doesn't really matter which one. Actually, this probably is good if I rewrite it 0 as a root. Right, and I have a 2. 2, I have a 1. Right, 1, I have a 3. And 2 also have a 4. Right? And then if we go from 0, 0 is a 1. So I know it cannot be split by itself. And then it passed down the 1 value to this. Right? It passed it down. So now at this position, I have the thing passing down like a carry. So the carry is 1. And then myself is 1 as well. So for me, I can choose to sever, but then that doesn't work, right? Because, yeah, it doesn't work. Or I can choose to sever on one side. Okay, let's just say we sever on this side. And then we'll keep going. And this basically will do that. And this will give you 0. This actually not only give you 0, it doesn't work. Alright, it doesn't work. So once it comes back, it doesn't work. So yeah, this doesn't work. So all you can say, we will sever that side. And then this works and this works. So what if you sever that side and it returns? It still doesn't work. Alright, what if it still doesn't work? That means you cannot sever. And then that's the answer. It's just 1. Alright? Does that make sense? Like every position you do 3, but will this be a DP level? I mean, for each one, if we go DP, that will be the index, right? And also carry. But this could be huge. Index is this much. Carry basically is carry can be a value or it can be just a modulo, right? Carry can be a modulo, which means it can be 10 to the 9th. That seems That seems pretty bad. Yeah. Peace. Yeah, that doesn't seem to work. You have a lot of index. You can have lots of carry as well. If it has to be divisible, right, then it's guaranteed, right? If you have a tree can get into 3 different components and each one of them is divisible, then you add them together is divisible, and then you add them 3 together is also divisible, right? So now I have a question. Would it be possible that we create a tree that, because like the sum of this must be divisible. So here is a little experiment. Would it be possible that, we'll change a little bit. So we'll copy and paste this, but change one value. Now this is not divisible. The sum become 19. Let's see what's gonna tell us. Yeah, it has to be divisible, right? So the total is divisible, which means all we want to do is to find the smallest from the bottom up. The smallest one that's divisible, then the rest is also, it's guaranteed to be divisible. It's kind of a little bit greedy, right? Because we can say if we don't take the smallest, right? We take a little bit bigger. And then there's an argument is we can always break it and then break it, right? So yeah, that's what you should do. You should go from the leaf up, right? Find the first one that's divisible, sever it, and then keep finding. So you will be going all the way down at each root, right? At each node, you want to know what is the sum of your subtree, right? If the subtree is divisible, you sever it. Don't even worry about it, right? You just sever it, and you will return 0, right? You will return 0 to your parent because this is severed. That seems to be possible. Let's try this. Since each component sum must be divisible by k, after one component is removed, the sum, right, of the rest. Hold a second. Right, the sum of the rest is still divisible by k. Thus, we just need to continuously remove the smallest subtree whose sum is divisible by k. And it's guaranteed, right? So I think it's on. We do need a recursion on this, unless we want to well, we do need to have, because every time it's divisible, I return a 0, right? So like I find out that I'm divisible, so that should be plus plus. The result should be plus plus, and I return a 0. So I have a result here, right? And then I will have a std function, right? Or have a return an int and input an int as well, a DFS. We take a reference index, right? Or have an index, and then we'll return a and then we also need to have a map with call that a graph. Edge of edges. We say graph edge 0, pushback h1, h1, pushback h0. Okay, so we have the graph. Okay, so now what we need to do is go through. We want to know if my subtree sum, right? Subtree sum. So I need to go to the left and go to the right. Not just left. Just go through all of them, get their return back. So we say int s is gonna be myself, values index. Actually, to make this more possible, let's go long on this just in case. All right, so this is my current, and then what do? I will go for my left, so I say for int child. But you also have a parent, so I need a parent as well, just in case. So int parent, so I need another int here. So for int child of graph index, if child not equal to parent, then what we do is we'll do DFS child index, and we say s will equal to s plus this. Ooh, then it's not int, it's gonna be a long, right? And then we'll mod k. Right, so s blah blah blah, go through everybody, and then when I come out, we say if s is equal to 0, then we'll split. And by split, I mean rest of plus plus, because I am splitting, and I'll return 0. So split, right? Split the subtree, rooted at index. Otherwise, right, I'm not. Then we just return s. I probably got this one wrong. Let me C++ lambda function definition with 2 int as argument and long as return. Yeah, I want the definition. Give me the function type. I need the function type using std function, because I have to. That looks like what I have. Wait, hold on. S is long, right? Oh, but this is. Is this? I forgot. No. Which is wrong, right? Do I have to long this one? I don't understand. Has unspecified explicit return type. What does this mean? Do I have to log on this k as well? No? What the hell? Oh, I think it asked me to be explicit. So maybe I need to do this. Ah, so that's what's missing. Okay. Yeah, that's fine. So we then do DFS. Yeah, we start from 0. Parent is gonna be -1. And then we return res. Okay, I have no idea. We'll have to go take a look. Yeah, this is not gonna work. Okay, this might work. I bloody did not. Huh. Okay, so no edges, just the root by itself. And then we call the root s is equal to the value. I think here is wrong. S should be mod k. There we go. Pretty slow, but it works. Okay, I want to see the solution I had in the past. Like, what did they look like? 2021. Yeah, greedy. It's the same, but wow, I think the improvement is on how much less code is needed. Let's go back. Oh my god, this is just stupid. What the hell? Oh, I hate these UIs. Absolutely stupid. Oh, you don't need to use a map. Darn. Oh, yes. That is true. Yeah, it's the same idea, but what the hell is this? Oh, array of array. I see. Okay, I can do that. I can do that. All I need to do is do. Yeah, I was like, I didn't use I only used the n actually. Vector int graph. Yeah, I think this will be fine. Then I don't need this. Everything should still work. Yeah. Update. Use an array of array for graph instead of map. This should improve performance. Also here, yeah, this is split. Okay, let's see if it improves. A little bit. A little bit. 175, 22.7%. Nah, it's good enough. Let's call it a day. Okay, that's it. You're gonna BFS. Oh, topological sort.